This workshop is about algebraic structures and quantum computation. Now, when I saw this title, I was a little bit afraid because I'm not really working on algebraic structures and quantum computation. So some algebraic structures will occur in this talk at the end. So my talk will be about entanglement, or a little bit about something like quantify. I called it quantifying entanglement from the geometric perspective. And essentially, it's about something like some geometric view of entanglement, where you essentially try to, what's called some of the geometric measure of entanglement, and some related quantities. And this is, first, this is a series of works which we're doing now, or have been done recently. Just to introduce you my courses. So essentially, all of these people have been in Siegen for some time. So Sophia Denker is a PhD student in my group. Satoya was a PhD student in my group. Now he's in Florence in Italy and will move soon to Tsukuba in Japan. Ismail is a postdoc in my group. Jonathan was a postdoc, was a PhD student in my group, but now he's a patent attorney in Munich. Lisa Weinbrenner is a PhD student in my group, and Xiao Dongyu was a postdoc in my group, but now he's in Jinan in China. What I will talk about? I will talk about only 4 parts, and I try to be as introductory as possible. So I don't have many results. I'm just telling you a little bit what we are doing. So the first one, I try to be introductory, so please also interrupt me at any point. We have 1 hour for the talk, which is quite a long time. So just interrupt me whenever you have questions. So first I will talk a little bit about the geometric measure of entanglement, just as in some introductory work. And then I will tell you why this may be interesting. Then I will talk about with Jonathan, which is about how you can find some maximally entangled states. Then I talk about 2 ongoing projects. Essentially, one is about maximally entangled subspaces, and one is about some methods of computing this measure with some trick on multiple copies. During my talk, I realized that I don't have many pictures. So I try to counteract by that by showing you some pictures of Siegen. And so this is essentially the main church in Siegen. Let's start. So let's start with the geometric measure. And this is the bigger see, which is also close to Siegen, which is one artificial lake. What is the geometric measure? In principle, it's very simple. You take some quantum state, for instance, on Alice, Bob, and Charlie, and you just look for the maximal overlap with product states. This is somehow just the definition. You maximize this overlap with product states, and of course, if the state itself is a product state, then its overlap is 1. So then it's maybe not so much entangled. And if the state is maybe highly entangled, then you cannot get a high overlap. That's the idea. And then, of course, you just take 1 minus this number and call it the geometric measure of entanglement. Okay, so this brings me to this point. I will focus on 2 and 3 parties for simplicity. And you may also ask what happens to mixed states. So in mixed states, entanglement measures for mixed states are complicated. And one can do something that is called something like the convex roof. You have to try to minimize all decompositions that you have. But actually, also in my talk, I will not talk about mixed states. So I just will make it as simple as possible, just about pure states and 3 parties roughly. Just do some examples. Very simple. So let's start with the bipartite state. And for bipartite state, you have something like a Schmidt decomposition. And you can easily show that this maximal overlap with product states is just taking the biggest Schmidt coefficient squared. And essentially you take just this, for instance, 0, 0 is maybe the maximal Schmidt coefficient. Then you just take this overlap with this state and you get this into square root. This is actually 2 lines proof. Let's take the next example. Let's take the GZ state. The GZ state is, probably have seen that before. And for this GZ state, you can argue as follows. First, we can somehow relax this optimization problem and do not optimize over fully product states, but over biseparable states, which is a larger set, so the bound will be larger. But then we see, because the Schmidt decomposition is already written here, that even with these states, we can only get a value of 1/2. And because this is Schmidt coefficient, if we square it, it's 1/2. And then you see that this bound can actually also be reached by a fully product state. And this means that this bound is 1/2. So that's just a simple calculation. Next example. Now let's assume that the state is symmetric. Yeah, and so it means that should be the projectional symmetric subspace, and yeah, you have something like a symmetric state where all the particles are essentially the same. And for this, you can prove that actually it's sufficient to maximize over all symmetric product states also. Yeah, actually, this sounds very simple. Yeah, and in some sense it is simple, but actually proving this is not so simple. But yes. So, and how does it help? For instance, let's take now the W state. The W state is given by this state. And you see it's obviously symmetric. And if you would do this bipartition as before, you would get some number, but actually this would not be optimal. But if you now maximize this overlap with these kind of symmetric states, yes, and actually you have only one parameter left in the entire optimization, and then it's easy to solve, and then you see that this state has a maximal value of 4/9, which means that it's smaller than 1/2. So the overlap with product states is smaller than the jet set state. And in this reverse picture, they take 1 minus that. It somehow means that the W state is more entangled than the jet set state. So these were just simple examples. Now let's make it a little bit more complicated and ask for a general state. And in principle, one can actually show that for a general state, I think this is some NP hard problem. Yeah, so it is definitely a hard problem, but there's a simple numerical optimization that works very well in practice. And since we also will later use this, I shortly explain it. So the idea is to make such a seesaw-like algorithm. Yeah? So if you take some state and you fix a state for Bob and a state for Charlie, then you can just compute the remaining state on Alice's side. And of course, now if you optimize then for Alice's vector, it's clear that the optimum has to be essentially proportional to this state. This is not necessarily normalized, you have just to normalize it. And that means for given B and C, the optimal A is clearly easy to compute. And then you can just iterate. Yeah, for you fix B and C, you optimize over A. Then you fix A and C, optimize over B. And then you iterate. And of course, I should stress that this is, of course, not guaranteed to give you the optimal value. Yeah, it's just a monotonous approximation. It's a monotonous increasing function. But this is not, I mean, there may be some local maxima, whatever. Yeah? However, I'm just telling you, and of course, this is just the language of physicists, it works well. Yeah, for up to 8 qubits, you can more or less trust this. After that, you run into some numerical optimization problems. First, it's getting slow. Second, it's at some point you see a lot of local maxima. Yeah, but roughly for small qubit numbers, this works well. Let's talk a little bit more about some properties of this measure. So first, I mean, as a physicist, you may ask, what's the interpretation? And there are a bunch of interpretations, and one of them is, for instance, that this is related to the distinguishability of some set of states with local measurements. Yeah, if you have some certain states and you want to distinguish them locally, yeah, by some local operations, then you can prove that if they have a high geometric measure, it's hard. Yeah, and this is really it's a formula that you can somehow, the success probability you can bound by this geometric measure, essentially. Second property, of course, this notion of the geometric measure is in some sense not new. Yeah, meaning that, of course, mathematicians have thought about that before physicists do. Yeah, and this is sometimes called in tensor analysis, it's something called the injective tensor norm, and it's related to some definitions of tensor eigenvalues. So if you go to the math literature, there's a lot of literature about that, often in a little bit specific settings because they often assume certain symmetries and so on. Yeah, but there's a lot of literature about that. Okay, I will comment on this a little bit also later. Then you may ask, what's the entanglement of a typical state? And there it has been shown that essentially if you have a generic state of many particles, they're very highly entangled. So they're really far away from the product state, and actually you do not have to do the optimization of products anymore. You can just more or less take a random product state and it will give you already the correct value. Yeah. So I mean, this is just some example of which we just once did numerically. So if you take different numbers of qubits and you look essentially at the geometric measure, which is 1 minus the overlap, be careful, then you see, for instance, that for n equal to 7, more or less, all the states have a geometric measure between 0.8 and 1, or close to 1. Yeah, this is somehow this. But there are some rigorous results here which really proves this for. Let's go on. There are some generalizations. Because in principle, so far, we looked at something like overlaps with the fully product states. But of course, you can look at overlaps with other families of states. Yeah, so in principle, let's call it maybe theta. Yeah, and you just have such an overlap. And there are different candidates that you can do if you want to characterize entanglement. For instance, what you can do, you can look at biseparable states, where the states is separable for either for this bipartition, or for this bipartition, or for this bipartition. Then you can look at states with fixed tensor rank. So in the sense that you say, okay, it's not a one component product state, but essentially you have superposition of two components, or more, or whatever. You can fix this number, whatever you like, and this is called the tensor rank of a state. And in principle, you can also say that if your state is on two of these components, then it's also not very highly entangled. And then you can look at the overlap with this kind of states. Or what we are currently, for instance, studying is something like the superposition of biseparable states. Yeah, we essentially allow not this fixed, not fixed number of terms, but they may be biseparable with respect to different bipartitions. So what I'm saying is that there's different sets of states that you can take and try to compute this overlap. And they all tell you something about the entanglement that you have, in a sense, how far you're away from a certain class of separable states. And what I also should stress that more or less all these problems are equivalent to the standard optimization that I introduced on the first slide. Yeah, so it's not a big difference whether you take this one or this one. You can often go to some multi-copy space and then map it to the standard optimization problem. And maybe with some extra constraint and so on. So it's not directly equivalent, but it's quite related. Yeah, and also, for instance, if you want to optimize some overlap between local unitaries, actually you can also map it to such a problem. So what I want to say is essentially that this kind of optimization over this product states is quite generic. In a sense, if you know something about this kind of optimization, you can use it for different tasks. Let's come now to the overview of this talk, and I will discuss 3 questions. Yeah, so the first question is now, how can we find some maximally entangled states? So how do we find, for instance, for 5 qubits, the state that is furthest away from all the product states? Yeah, for 3 qubits, I told you this is a W state, or at least the W state is more entangled than the Z state, but what happens for 5 qubits? Yeah, of course, you can write down hundreds of 5 qubit states, but it's unlikely that you will manage to get the right states from the beginning. Then, based on that, I will talk a little bit about some subspaces that you can identify, where all the states are highly entangled. And finally, I will present, as mentioned, some tricks how to compute the geometric measure or related stuff for general pure states. Concerning the picture, this is this Atterhöhle, which is a huge cave, also quite close. Let's start with the first topic. This is how to find the maximum entangled states. The idea is very simple. The idea is as follows. So let's assume that you have some state. Let's call it phi. And you want to optimize the overlap between this state and this product state, which are maybe the blue states here. Yeah, there's some manifold. And let's assume you have the state and you know that the closest product set is this pi. What you can then do there is the following. You can compute the component of this phi in the direction which is orthogonal to this. Yeah, so essentially you take this state and project it onto the orthogonal space of this psi. That means you compute this component going orthogonal to this pi. And somehow from the intuition, you may believe that, well, if I go in this direction, then the geometric measure can only increase. The distance has to increase, yeah, because I know that this is the closest point, so I'm going in the opposite direction. So the intuition says, well, this is the right direction to go if you want to maximize this measure. Yeah, so what do you then do? You essentially shift the state in this direction. You take this phi, you go to some phi tilde. Yeah, and which is just phi plus some epsilon eta, and you have to choose the epsilon. You maybe choose it small, maybe, yeah, a very small number. And of course, you have to renormalize because this is not a normal. And this is the basic idea that we try to find a state that is far away from the separable states. Yeah, so you just compute the closest state, and go in the opposite direction. Go always a little bit in this direction, and yes, yeah, and I hope that it increases. This is, of course, a naive picture, and now you have to prove that it really works. And actually, you can prove that it works. Yeah, so the result is the following. If this closest product state is unique, and the epsilon that you take, that this means this one, is small enough. Yeah, so if this state is unique, and this is small enough, then it works. Yeah, then you can rigorously prove that essentially this distance increases. And this means that essentially this gives you something like a strict monotonously increasing sequence of states, yeah, where this geometric measure increases or the overlap with the product state decreases. Then, of course, you can ask, oh, what, does it work in practice? And the answer is, well, this is a physicist's answer, it works quite well. Yeah, surprisingly well, I would say. Yeah, so for instance, you can take, this is for 3 qubits, you take some random input states which have partly a very small overlap. Then you do this kind of iteration, yeah, and then you see that after typically something like 300 iteration, you really arrive at a state which has a geometric value of 0.55, this is the number, and 0.55 is 5 over 9, which is 1 minus 4 over 9, which is this W state that we had. So, and you also see that here maybe you see, so this is nicely monotonously increasing, and here you see for this state you see this a little bit wiggling around. It doesn't seem to increase monotonically, but this is just because you're choosing this epsilon too large. Yeah, if you of course take epsilon too large, then at some point you're going a little bit away from it. But what you see that essentially this works quite well with a short number of iterations. You find some states that are highly. Then actually I just see that this is the wrong way around. So of course this decreases. And the overlap decreases and the geometric measure increases. Let's take some results. So first, I mean, this is now the simplest thing that you can do, that you just take qubits, and now we take more than 3 qubits, we take up to 7 qubits, because after that it's getting slow. And we just ask for the state that maximizes that we find in this procedure. Yeah, which seems to maximize the geometric measure. And of course, well, for 2 qubits, we find just the Bell state. For 3 qubits, we find the W state, yeah, which I also explained before. And then for more qubits, we find something. For 4 qubits, we find some state that it's called the M state, it was called in the literature, which is actually a state maximizing, which has a one-body marginals maximally mixed, but the 2-body marginals cannot be all maximally mixed, but still the entropy is maximized. Yeah, and this M state looks roughly, you can, for instance, write it like that. It's a superposition of G at Z states where you flip some of the qubits and you also put some phases there. There are different ways to write the state. Yeah? But this seems to maximize this geometric measure with this value. And for 5 and 6 qubits, we get graph states. Yeah, which is here for 5 qubits is a ring cluster graph states. For 6 qubits is the AME state, this graph state. And for 7 qubits, okay, we don't get a state which we actually did not find in the literature. Yeah, so it's something like a state where all the 1 and 2 body marginals are maximally mixed, but the 3 body marginals are not all maximally mixed, but they have still a high entropy. So this at least shows that you can identify some interesting states, yeah, or at least prove that they have some interesting properties. This column you can forget because people have considered this question before by assuming that the states are symmetric. Yeah, and of course this is a strong constraint, and then you don't get so high values for the geometric measure. Then you can ask for some further applications. So one thing is you can ask for the connection to AME states. What are AME states? Well, AME states are called absolutely maximally entangled. Actually, I don't like this word. It sounds a little bit ridiculous, but people have introduced it before we did. So we also use it, yeah. And what is an AME state? An AME state is defined by the property that all bipartitions are maximally entangled. Yeah, for instance, for 6 qubits, you want all bipartition of 3 qubits versus 3 qubits should be maximally entangled. And they do not exist always. Yeah, and there has been a bunch of discussions. This has been flagged as one of the 5 important problems in quantum information theory where certain AME states exist, and this has been solved quite recently by Karol Trzaskowski and his group. And it seems that AME states are also typically candidates of maximizing the geometric measure. So I think many of the states that we identify were AME states. And actually we also find this maybe interesting, some AME states that were not known before. I mean, In a sense, there was known that some AME state exists, but we found some other AME states that also exist. So in principle, these AME states are not unique. Another observation that is maybe relevant is the following. This whole algorithm that I told you does not rely on the property that this state is a product state. I was always just maximizing the overlap with states from some manifold. I did not do anything about the product structure was not assumed. Yeah, in the numerics, of course, we used it somehow. But this theorem that you can, with this type of algorithm, always increase the distance works for any manifold. And then we can, of course, use it for some other things. Yeah. For instance, what we tried and what we maybe want to try further is something to maximize the distance to some states with some small stabilizer rank, or also maximize the distance to some matrix product states with a small bond dimension. Yeah, I'm just saying that you can take other families of states and also try to find states that are maximally far away from it, which is essentially the same. Let's come to the next part, and which is now about entangled subspaces. And here the question is, can we find entire spaces where everything is entangled? And okay, this is a picture, this is a Freud's book also. What do I mean by maximal entangled subspaces? I can, for instance, look for some two-dimensional space such that all states in the space, or the entire space, has a small overlap with product states. So before I was essentially looking for a one-dimensional space, namely one projector onto some state, where I want to say, look, this should have a small overlap. But I can just look for two-dimensional spaces. And actually, one can use similar tricks as before to essentially take one space and then rotate it in a certain direction that this overlap does not increase. And then you can try. And actually, for 3 qubits, it works quite well. It's getting numerically a little bit more complicated, as you could imagine, because it's getting more and more parameters. But essentially, you can take such a space and also try to rotate in a direction where this overlap becomes smaller. And then you can iterate and try to find some space. And this is also what Jonathan did. And the somewhat surprising result is the following. That actually, if you take somewhat like a superposition of 2 W states, so this is one W state with some, and this is another W state, where here the zeros and ones are flipped, and you introduce some phases which are roots of unity. What can then directly see? These 2 vectors are orthogonal, they span a 2-dimensional space, and all states in this space are maximally entangled. So essentially, for 3 qubits, we do not only have one maximally entangled state, we have an entire 2-dimensional space where everything is maximally entangled. Yeah? And yes, so this is somewhat a surprising result because, well, we do not expect that this entire space, but it just happens to be there. And then we were thinking a little bit further, is this space useful for something, or is it somehow, did it occur somewhere else? And actually it occurred a little bit more recently after our paper. People asked for the following. I mean, there's something which is called the swap test, which means if you take a density matrix and you want to measure trace rho squared, something like the purity. What you can do, you take two copies of a density matrix and make a swap gate, and then essentially, or conditional swap gate, and then measure on one of the qubits, and with that you can essentially measure trace rho squared. This is a common trick that people use for many instances. And there were some works how to try to generalize it in order to measure something like trace rho to the power of 3. Yeah, and this is this work here. And it turns out that essentially for measuring trace rho to the power of 3, you directly have to measure the projector onto the subspace. Yeah, so in principle, again, this occurred somewhere, and if you can understand it, because some of this can be seen as a generalization of the swap test, is something like measuring something like in some Bell basis. Yeah, and this for 3 particles, you have to measure something else, but essentially this can be the same subspace occurs in something like generalized of the swap test. And this is somehow for us was surprising, but so okay, it may be a little bit useful. But then, of course, the question is, can we understand this more generally? Yeah, because I mean, okay, it's still an example. Yeah, and can we understand it? And the way to understand it is the following. If you take this shift operator for 3 qubits, you take something like, you just shift the qubit ijk to kij. Shift essentially the qubits in one direction. Then you can look at the operator, and it has 3 eigenspaces. There are, of course, states that are symmetric under this shift, which are the symmetrics. they're invariant, which means there's a symmetric space. And there are states that essentially get a phase of omega and states with a phase of omega squared. And essentially this subspace, giving this phase of omega, is nothing but the space from above. Because if you shift them here, you get essentially a phase of omega. That means that essentially the eigenspaces of this shift operator are just these highly entangled subspaces. And this is, of course, motivating because now we try to understand some structure. Yes, it's not just by random putting, it's simply related to this exchange symmetry. So, and then you can go further and try to generalize it. In principle, for instance, if you have 3 qubits, you have different kinds of spaces. You have something like the symmetric space, you have the antisymmetric space, and you have 2 subspaces which are sometimes called chiral subspaces. Again, this was not invented by us, but people called it like that, so we also call it like that. And this essentially this, which gets a phase of omega via a shift or something like a phase of omega squared. And what we then can prove that in these subspaces just have the general property that they are very high dimensional spaces, but all the states in the space are highly entangled. Yeah, so this is quite a general property of these symmetries. Yeah, and you can also split this space further where you have one subspace which has even higher entanglement. Yeah, so in principle, using the symmetries, you can identify some highly symmetric spaces. And for instance, then if you took a similar argument, you can look for the antisymmetric space and you also get something like a bound on the overlap, which means that general antisymmetric states are also highly entangled. Let's come to the last part of my talk. The next thing is about how we can, let's go a bit back just to the original problem where we want to compute this overlap with some product states. And I told you this is a hard problem. I mean, we have some numerical optimizations, yeah, but in principle, can we do make some rigorous statement? If you want to do that, there's some trick. And actually, this trick we discovered, actually when René was still in Hanover. There's a paper by mathematician Shmuel Friedland, and the paper is very mathematical. Let's put it like that. It talks a lot about polynomial rings, about symmetric polynomials, and so on. And in the end, the main part of the paper, I would say, are these 4 lines. And they are a trick to estimate this overlap. And it's a nice trick. Essentially, the idea is to go to several copies. So, for instance, I mean, you want to compute this overlap of ABC with phi. Now you just take essentially 2 times phi and 2 times the state. And of course, well, it's the same, because you have the square. Now, you have somehow that on this part of the system, here you have a symmetric state, A and A. And here on Bob's part, you have B and B. This is also symmetric on Bob's part, and this C and C is symmetric on Charlie's part. So what you can do, because Alice has now 2 particles. Alice has these 2 particles, and she has a symmetric state there. So what you can do, you can insert here something like a projector onto the symmetric subspace. Then you can do the same for Bob, and you can do the same for Charlie. Yeah, these are something like on the 2 copy space, these are symmetric projectors on these 2 things, these 2 things, and these 2 things. Yeah, so nothing changes. But now, you can essentially let these projectors act onto this state. And actually here, I mean, this state is not invariant under these guys. So what you then can do is essentially, okay, you take this, you insert this projectors, nothing changes. But then you say essentially relax this condition of being here product state by putting here an arbitrary state. But let these projectors just mainly work, act on this thing. And then, well, the maximum of a general state here is nothing but the norm of the state. So essentially, by just going to a 2-copy state and inserting these projectors, you get a bound on this number, which is very cheap. Yeah, because you just write it down, you get a bound on this. You just have to look at this 2-copy vector, insert the projector, you get another vector, compute the norm, and this gives you a bound on this number. And if this is essentially, I wrote carefully hidden behind algebraic structures, because this is where algebraic structures occur. And actually, if you look in the paper, you will not. It's not so easy to find this trick. But this is a way how to estimate this thing. And of course, once you have this, it's easy to go to more copies, because it's easy to write down the same argument with 3 copies or 4 copies or 5 copies, whatever. And actually, also, it's easy to go to other permutations. You can wire them differently and so on, and make here some other permutation operators whatsoever. There are a lot of tricks that you can play around with. Yeah, so the question is, how useful is this trick? I mean, okay, as mentioned, this is a mathematical paper. There's, of course, no example in this paper. Good. So, and to use now really where this trick really works in practice, what we did is the following. This is an old question entanglement theory which is about unextendable product basis. So what is an unextendable product basis? Well, if you take a bipartite 3×3 space, you can write down 5 product vectors. Yes, this is 0 on Alice's side, 0, -1 on Bob's side. This is 2 and so on. These are 5 product vectors. And they're sometimes called tiles because you can write here 0, 1, 2, and then it's 0 and these things, and somehow these vectors correspond to something like tiles here. Yeah, okay, this is just to memorize these things. Anyways, these are 5 product vectors, and there's the following nice properties. There's no product vector orthogonal to all of them. Yeah, so that's what it means. It's an unextendable product basis. Yeah, you cannot extend it with more product vectors to make a basis. Yeah, of course, it's a little bit misleading because, of course, these 5 vectors are not a basis. There's only 5 vectors. You need 9. Yeah, but in a way, so essentially, you cannot make this set of vectors larger to a full product. Why is this interesting? This occurred in several contexts, similar constructions, and the point is the following. If you take now the orthogonal space of this thing, this does not contain any product vector, by definition. And actually this means that this more or less the orthogonal space is roughly, if you normalize it, it's an entangled state. And it's an interesting entangled state because it's PPT entangled, it's bound entangled, and so in a sense you cannot detect it so easily by other criteria. Yeah, and this was an old paper by Charlie Bennett and Barbara Terl and so on. What is now the question? We know that in this space there is no product vector. But we want to know how close can we get with product vectors. So in a sense, what is the maximal overlap between product vectors and the space? It cannot be 1 because there is none. But is it 99% or is it 80% or whatever? So what we want to know is we take this space and want to take the maximal overlap with some product vectors. And this is important for constructing, for instance, witnesses and so on. And yes, and for instance, it is known that one has an analytical bound of 0.99. This was a paper by Terl, and if you do some numerics, you get a better value of 0.97. But of course, this is not a rigorous statement, and this is only the analytical statement. What do we have to do? Well, we just use our trick. We take several copies of this guy. We take projections onto symmetric spaces onto several copies. And we compute the maximum eigenvalue. And this, according to this reasoning on the slide before, should give us essentially a bound on this delta. And this is now very easy. I mean, you just take a matrix, you take several copies, you symmetrize a little bit, and you just calculate eigenvalues. So in principle, this is an easy task. And what you then find, for instance, if you take 3 copies, you get something like a 98%, which is already better than the known before. And for 4 copies, you get even a better value, and so on. Yeah, so you can use this, at least in the simple example, to show already it gives you some insights that was not known before. This is one thing that we're currently working on, how to increase this further and to use it for other scenarios also. But this shows that there's something possible. That's essentially all that I wanted to tell you. I hope I convinced you that this geometrical measure is somehow interesting from some physical as well from a mathematical perspective. Yeah, so people as well in mathematics as in physics, they considered that. So in principle, it's useful to study that. And also one of the points is that what I mentioned, that several other optimization problems can essentially be reduced to this optimization problem. Yeah, so it's not a specific optimization problem for states, but it's something like a general thing that occurs in several contexts. And then, essentially in the main part, I told you 3 different things. Yeah, so first you can systematically identify some highly entangled states or highly entangled tensors, or tensors with a small injective tensor norm, how the mathematicians would say that. Using symmetries, you can find some highly entangled subspaces, and also with this tricks on multiple copies, there's some way to give some rigorous bounds on these quantities. Okay, that's all I want to tell you. So there's one publication which you find on the archive in the journal, and there's something coming out hopefully soon.